So lecture 4 today, 4A, will start by reviewing linear and exponential functions, what we've talked about so far. We will probably get a little bit into function composition as well, where you are combining functions by plugging one function into another. That's one way to conceptualize it. Another way to conceptualize it is to apply one function right after the other. And then in lecture 4B, continue that, including inverse functions. I didn't put that in there, I probably should have. Maybe I'll do it after class before I put it on the Google folder for you to look at. I'll probably add that we're talking about inverse functions in lecture 4B. Then we'll talk about a particular kind of function, quadratic functions, and transformations of graphs, like horizontal shifts, vertical shifts, that kind of thing. To start the review, let's look at one of these, well, maybe two of them. We'll look at this one together here today, number 3, one of these ones that I made a key for. Since I had trouble with the Mathematica last time, let's also redo the Mathematica. And I think I probably will add to one of your completion assignments this week. Maybe do Wednesday, maybe do Friday. I'll probably add a Mathematica one. And you'll need to get into Mathematica and actually do it and print it out as part of your completion assignment. I'll give you more details about that on Moodle. Let's go ahead and do number 3 and 4, and probably number 5 as well. Those would be good to do here. So number 3 says, find an equation of the exponential function passing through the points -4, 324, and 2, 4 ninths. Okay, so maybe we can draw a graph, but the scale is going to be such that it's not really going to be a very accurate graph. This is going to be an exponential decay function, because when x is -4, y is very large. But when x gets bigger, up to 2, y gets very small. This is going to be a exponential decay function, like that. By the way, a bit of calculus words here. You'd say this function is decreasing. Its slopes are always negative. It's going downward as you move to the right here. And you'd also say it's concave up. So decreasing and concave up. A couple of calculus terms. Concave up essentially means it looks like a smile or a part of a smile. Okay, right? That's half a smile there. The slope, technically speaking, is getting larger, though it stays negative the whole time here. It's getting closer and closer to 0. That's what concave up means. And so again, I'll kind of draw these points, but this is not to scale by any means. Pretend this is -4, 324, and this is 2, 4 ninths, but definitely that's a bad scale, okay? So don't take that too literally. It's an exponential function, so it's got the form a times b to the x. We'd like to solve for a and b. That's the goal. You need to use the information you're given. You plug the numbers in. When x is -4, y is 324. I'm doing this by solving for a and b, whereas in my answer key I solve for a and b number 2. Number 2, and then I used a reflection property to solve for number 3. The second point is that when x is 2, y is 4 ninths. So 4 ninths equals f of 2 equals a times b squared. Solve for a and b. It doesn't look like it's going to be very easy to solve for a and b, but it is possible, and you should be able to do this for Wednesday's quiz, probably with a little simpler numbers. In this kind of situation, it's a good idea to divide one equation by the other, because if you do, the a's will cancel, and you'll be able to combine the exponents of the b. So, for example, if you take the first equation, divide it by the second. On the left side, you'll get 324 divided by 4 ninths, which is 324 times 9/4. And on the right side, you'll get a times b to the -4 divided by a times b squared. The a's completely cancel. And with these exponents, when you've got a b to a power up top and a b to another power down the bottom, you can write it as b to a power where you subtract the exponents, -4 minus 2, b to the -6. There's a negative power there. Haven't made any mistake, hopefully. That's the right answer so far. Again, this is the same as 324 times 9/4, or 324 times 2.25. We can also cancel the 4 with the 324. Let's see, divide that by 2, you get 162. Divide by 2 again, you'll get 81. Reminds me of baseball. There's 162 games in a season. It's just something I remember. 81 times 9 is 729. So 729 equals b to the negative 6. If you prefer, you can write that as b to the positive 6 is 1 over 729. B is going to be a number between 0 and 1. Now you can guess the answer here. You might guess 1/3 for B. Maybe that's not obvious. 3 to the 6th power is indeed 729. 1/3 to the 6th power would be 1 over 729. So B is 1/3. If you weren't sure, you could take 1 over 729. It's about 0.001371741, raise it to the 1/6 power, and 1/6 is 0.16 repeating. You could do that. And if you do that, you do get 0.3 repeating, 1/3. But you really should know 729 is the power of 3. You should. I mean, I'm sure some of you don't remember that, but that's something that you maybe have done enough of that you've seen before. Okay. If you didn't know that, now I'm telling you. This is an example of, if I put it on the quiz, I probably wouldn't make the numbers quite so challenging to deal with. And then as far as finding A, you can use either of these equations and solve for A. It doesn't matter which one you use. Let's use the first one. Multiply both sides of that by b to the 4th. A will be 324 times b to the 4th. 324 times 1/3 to the 4th, which is the same as 1 over 3 to the 4th. I'm getting the 4 there. 3 to the 4th is 81. That's maybe something that should be more easily memorized. That's 4. So the answer is f of x equals 4 times 1/3 to the x, which is more commonly written as 4 times 3 to the negative x. That's the more common way to write that. All right, let's do the Mathematica one here. 5e to the 3t equals 17. I do know what I did wrong last time. Sometimes Mathematica is a little too fancy for its own good, and that's the situation here. There's a reason it's too fancy. It's because they want you to be able to do fancy stuff with it. So again, solve, capital S-O-L-V-E, will solve equations. When they are solvable, some equations are not really solvable, or you at least have to approximate the answer instead of finding an exact representation. Type the equation in, 5e to the 3t. Capital E is the quickest way to get the number E in Mathematica. Don't use a lowercase e. Use a capital E.
Did you put the bracket there, or did that just come in?
I put that there. So I put the up pair thing above the 6, and then the 3t like that. When you're solving equations in Mathematica, you must use double equal signs. Using just one equal sign will mess things up and cause errors later on down the line, so don't do it. Remember to use double equal signs. 17. Solve for t. Now here's what I entered last time, and it was not so nice looking. Okay, this is an example of Mathematica just being extra fancy, introducing the fact that there are complex solutions of this involving the imaginary unit I. Yes, that is technically a better answer for more advanced math. If you don't know what the imaginary unit is, don't worry about it. We want a real answer, so we put reals here. Here's how I should have fixed it. Now, I think it will give me a warning still saying inverse functions are being used. Some answers might be missed, but no, it didn't do that. Okay. That does work. It's not as simple as it might be. Putting a //simplify with a capital S at the end will make it look nicer. I guess we did already verify this in class last Friday, so I won't bother doing that again, number 5. But just realize this is saying the answer is 1/3 natural log of 17/5. This is really ln. Why? Because the natural log is supernatural, so advanced mathematicians say we should just call it log instead of this funny ln thing. Because why would you use another logarithm? Log-based e is the best one to use. You might be scratching your head and wondering why it's the best one to use, but I'm telling you it is the best one to use in general. There is a way to get Mathematica to do log-based n, for example, but I'm not going to show it to you right now. By the way, ln, I think it's French, or log natural or something. So all the French, maybe all the French mathematicians still use ln, but we use log here. And capital L, by the way. And square brackets for input. Square brackets for inputs in Mathematica, not parentheses. Okay? So I'll probably have you do something basic like that, either for Wednesday or Friday's homework, and print it out. Just as another quick example, we can solve a linear function, a linear equation. 5t plus 4 equals 6 for t, and I don't need the extra comma reals because that will only have a real solution, 2/5. That's saying the answer is 2/5. Okay? So that's a basic use of Mathematica. Mathematica can do much fancier things, but I'm not going to show you right now. I do want to show you this visual again, because I think it is an important thing. The example from the visual you can see is f of x equals 2 times 1.5 to the x. So the a is 2 and the b is 1.5. This function has the property that, for example, when you add 2, last time in class I added delta x, an arbitrary thing. Delta x is 2 in this case. What happens? By a property of exponents, this is the same as this. You can split 1.5 to the x plus 2 power into 1.5 squared times 1.5 to the x. Then you can bring that 1.5 out in front and combine these two things to say those two things are f of x. 2 times 1.5 to the x, because that's what f of x is. And that's what the graph is illustrating. If I increase the input by 2, if I add 2 to it, the output gets multiplied by 1.5 squared, which is 2.25. And when you animate it, all that's doing is emphasizing it doesn't matter what x is. Okay, it doesn't matter what x is. 2.25, 1.5 squared is 2.25, which is a really 125% growth, so it more than doubles in size. That second y coordinate is more than twice as far away from the x-axis as this first one. This point is more than twice as far away from the x-axis than this one is. And that works no matter what axis. It would be 50% growth for every time x increases by 1, 1.5 to the first. As a multiplier would represent 50% growth. And again, it doesn't matter what x is. By the way, this is made with Mathematica, so this is an example, a little fancier thing you can do with Mathematica. Let's look at a real-life situation with data. Let's look at the U.S. gross domestic product, GDP it's called. Has it grown more like a linear function or an exponential function since 2009? GDP is essentially the value of all U.S. economic activity during a given year. It's a measure of the size of the economy. And here's the data. You don't have to write all that down. But just glance at it and say, hey, well, for one thing, it's going up. These numbers in trillions of dollars keep getting higher and higher. That should seem like a good thing, right? The economy is growing. But boy, another thing you should notice is looking at that table, it's difficult to tell whether it's linear or exponential growth. How in the world would you tell? We're going to look at a spreadsheet here, where I've got the data in here. And I'll share this with you as well. Remember that I said linear functions are built on addition? In the table I made last Friday, I had an L of x and an E of x, L for linear, E for exponential. And I kept adding 5 to the linear function to get the next output, and I kept multiplying by 5 to the exponential. Remember that? So linear functions are built on addition, and exponential functions are built on multiplication. So how can I use that information to figure out whether this is linear or exponential? If this is truly built on addition, then for these outputs here, I should keep adding approximately the same number to get the next output. How could I quickly find out if that's true? You could find by subtraction. Take this number minus this number. Watch where I'm pointing. Take this number minus this number, see what you get. Take this number minus this number, see what you get. Subtract successive outputs. Say, take this one minus this one, then this one minus this one, then this one minus this one. Keep subtracting outputs and see if the answers are approximately constant. They're not going to be exactly constant because real life data is messy and rarely follows linear trends exactly. But if they're approximately constant, we might be happy. C5 minus C4 would be a way you could type that into a spreadsheet. If you've never used a spreadsheet before, this may be new to you. Equal sign right there is going to have it do math, essentially. C5 is referring to whatever numbers in cell C5, column C, row 5. And I'm subtracting whatever numbers in C4. This is called a formula in a spreadsheet. And the magic about formulas in spreadsheets, once you enter this, is if I click and drag this downward for the other cells to do the other differences, it will automatically be the right thing. Let me show you. You can copy and paste, but you can also click and drag. Click and drag this downward. It's automatically doing the right thing. 0.543 is indeed this minus this. Maybe you want to use your calculator to check that. Like 14.992 minus 14.449, you should get 0.543. The next number, 0.551, should be this number, 15.543 minus 14.992. Yeah, I can even do that in my head. The next one, 0.654, is 16.197 minus 15.543. So this clicking and dragging of the formula automatically made those be correct. It essentially copied and pasted the formula with updates. If you look in the formula bar for cell D6 here, it says equals C6 minus C5. I never typed that. It automatically took my formula equals C5 and minus C4 and changed it to equal C6 minus C5 because that's a useful thing for what I'm doing right now, for one thing. I look at those numbers and I see they're definitely not constant. In fact, generally speaking, they're getting larger. That's the largest one there. So probably a linear model's not the best. It's maybe okay still. All these successive differences. What about an exponential model? Instead of successive differences, you want to do successive ratios. Or quotients. I'll call them ratios. Take this number divided by this number instead of minus. Equals C5 divided by C4 instead of equals C5 minus C4. I'll copy and paste that down as well. Are these approximately constant? They're not exactly constant. But you might say, generally speaking, they're a little bit closer to being constant than the other ones are. They're generally getting larger as well. But the difference between them is not so extreme as with these numbers. That's telling me an exponential model is probably capturing what's really going on better than a linear model. Let's look at some graphs of these things. Here's what a linear approximation to the GDP data looks like. It's not so bad. Okay? It's pretty close to those points. GDP in trillions of dollars versus year. However, as I say at the top there, it produces residuals, errors, that have a trend to them. Here are the residuals. Essentially, these things measure how high above or below the blue line the red dots are. This red dot, for example, is about 0.2 or 0.18 units above the blue line. This red dot here is barely above the blue line. It's about 0.06 units above the blue line. This red dot, however, is below the blue line a little bit. The residual is about negative 0.05. It's about 0.05 units below the blue line. The one that's furthest negatively is 2016. This one looks like it's about 0.2 units below. Its residual is negative 0.2. What do you think I mean by saying this residual here graph on the right has a pattern to it? They have a trend. What do you think I mean by that? It's not a real strong trend.
Trend being go ahead, that's good.
That's what this is, what you call the trend line. But I'm talking about the graph over here. I'm trying to say that, well, the residuals kind of go down, then they go back up. That's a trend. They're positive at first, then they're negative for a while before becoming positive. Okay? It's not a ton of data, but it seems like it may be some sort of trend. It's not random. Not random scatter above and below the line. They should be random for it to be the true capturing of the trend, for this to capture the true trend of the data. For an exponential, the residuals are more random, positively and negatively. Two positives, then a negative, then a positive, then a negative, then two positives, then two negatives, then a positive. Seem basically more random than these errors. This is an exponential graph. This blue curve is not a straight line anymore. You can see it's got a little bit of concavity to it, concave up slightly. It's doing a better job modeling the trend in the data. It's closer to exponential than linear. There's a downside. These residuals do seem to be getting further away from zero as the years go by. That probably means if we try to use this blue graph for the year 2019, probably we'd be wrong.
Are random residuals for exponential graphs good too? Or is that
Yeah, you always want random residuals.
Okay.
You want to think of the graph itself as being capturing the trend or the true nature of reality, so to speak. And the residuals are kind of like noise. If you've ever heard of that phrase, in any kind of data in real life, you're going to have some noise, some randomness to it. Okay? So I'm not going to have you come up with a formula for something like this. I'm just showing you the background of this to give you the big picture of how people think about this stuff in real life. They really are thinking about this like economists. They're thinking about this kind of thing a lot. The economy, even though it's an abstract idea, certainly has a lot of relevance to your life. If it's doing well versus badly, that affects your job prospects and that kind of thing. All right, about 5 more minutes here for lecture A. Let's start function composition. So this is content from section 1.3. This is new. Given two functions f and g, we can often combine them via function composition. It's not the only way to combine them. You could do arithmetic with them. You could add them. You could subtract them. You could multiply them and divide them. But here we are doing what's called composing. What does this mean? Conceptually, there's really 2 ways to think about it. One is this. The functions are applied one directly after the other. One function is applied directly after the other. They are applied in sequence. One function first, then the other function. Another way to conceptualize this is that you're plugging one function into the other. Probably a better way to say that is you're plugging the output of one function into the other function. It's probably better to say you're plugging the output of one function into the other function instead of saying you're plugging one function into the other. I'll tell you what I mean here in a minute. But loosely speaking, we can say we're plugging one function into the other. I won't shy away from saying that, even though it's technically not the best way to say it. This operation of function composition is not commutative. What does that mean? Anybody know? Not commutative. You want to say it? Or you can whisper it to me. You can't do it in reverse order? Sometimes that might be true, actually, depending on what types of inputs you're talking about. But for this class, you probably will be able to do it the other way. Well, I guess I told you the answer here. You get a different answer if you do it in the other order. With multiplying and adding numbers, that's commutative. You can multiply 4 times 2, that's 2 times 4, whatever, and you get the same answer. 4 plus 2 and 2 plus 4 are also the same. Subtraction and division are not commutative. But wait a minute. Isn't subtraction also addition? When I say 5 minus 3, can we think of that as addition? 5 plus negative 3? That's true. And that does equal negative 3 plus 5, which is 2. However, 3 minus 5 means something different. It means 3 plus negative 5. And so you get a different answer. You get negative 2. So even though subtraction can be thought of as addition, it's not commutative because 5 minus 3 really means something fundamentally different than 3 minus 5. Given two functions, we can form either, well, if they are f and g, we can either form either fog or goff. Okay, my high school teacher called them fog and goff. And I am, right now, for fun, calling them log and graph. But usually I won't say that. Usually I will say either F compose G, or maybe, if I'm feeling extra fancy, I'll say F circle G. G compose F or G circle F. I'd probably better say compose. The circle is not an O. It's also not really a circle. Wait a minute. You're telling me that's not a circle? It sure looks like a circle. It's really just a symbol that represents the operation. Just like plus represents adding and times, X or a dot represents multiplying. It's just a symbol that represents something. It's not literally meant to be a circle. Something else could have been used. Something fancy, I don't know, like treble clef. F treble clef G could have been the way we represent function composition, but it's a lot harder to make a treble clef, even though it's prettier. Okay, it's just a symbol representing. And how are these functions defined? By the following formulas, or formulae. Technically, formulae is the plural of formula. But I'm going to say formulas typically, as most people do. These two formulas. F circle G of X is F of G of X. And G circle F of X is G of F of X. When you look at F of G of X, you're thinking, if you're thinking in terms of the first way to, the second way to conceptualize it, right here, you'd be thinking, okay, I'm plugging G into F. Really, you're plugging the output of G, G of X, into F. If you're thinking in terms of being applied in sequence, G gets done first, then F. It goes from right to left, inside out. X first gets sent to G of X, which then gets sent to F of G of X. G gets applied first, then F. G of F of X, the other one, F is the inside function, G is the outside. You're plugging F into G, or really you're plugging the output of F, F of X, into G. You work from inside out, right to left. F is applied first. Then G. Subtle points, but really important to not get confused by. All right, let's take a break.